All systems are nominal. Initialize Genesis sequence.
All right. Yeah, welcome to this session, Trash Talk. I hope you all had a good conference so far. Good, that works. My name is Gerrit Grunwald. I'm working for Azul. We do JVMs, and this session is about garbage collection. Did anybody attend the other session today from Stefan Johansson? This was really more about all the improvements they did on the garbage collection since JDK 8, where this is more about what is garbage collection, right? So it's a little bit different. So what he covered in 10 minutes, this is the whole session. Okay, memory management in the JVM. It's automatic, right? So why care? Who's actively setting a garbage collector in production here in the audience? Okay, the rest just use the default, which is fine, I guess. Well, it has some impact on application performance, obviously. Also responsiveness of the application and system requirements, right, like memory and stuff like that. So it's good to know at least something about the basics of garbage collection. And I found out that when I talk to people at the booth and I ask them about the garbage collector, then they say, no idea. I know there is garbage collection, but what it is, I don't know. And so I thought it might make sense to have a little session about that. So we start with, everything you see is very simplified. So you should get the idea, right? So we start on the left, we have the so-called stack frames. They are bound to threads. They grow and shrink dynamically, so they are local access only, so are thread safe. We don't need garbage collection here. They only store primitives and references, right? So then we have the heap. The heap is where all the objects stored in memory, so they really consume memory. And this is shared access, so we need garbage collection here, and they are not thread safe. And then there is the so-called meter space, where we store class metadata, constant pool, method bytecode. So in short, everything the JVM needs to handle classes. But we don't look at the meter space here. We are only interested in the stack frames and in the heap. So I hope it's readable. Just very simple code, as you can see, a record of a person. I created 4 objects here, and then I add these objects to a list. That's it. And then I print just the P1, right, which is my name. So we have a stack frame for this thread, and we have all the references of these persons and for the list in the stack frame. So then we have the heap, and from the stack frame, we have references to the objects on the heap. And you see we have the person 1, P1, P2, P3, and the list object on the heap, and they take up space. So all of these objects are reachable from the stack frame, right? So you can just, every reference can be followed into the heap. So what happens if I, for example, set P1 to null? Then if I print out P1, it's null, but it's still reachable because there's still a reference in the list, right? So the list also points to that object on the heap. So it's still there. And I can get, as you can see in the code, I can get the result if I just ask the list for get 0 in this case, which is the first object. Well, that's fine. If I now remove by setting the list to null, then suddenly only the 3 objects in the middle are reachable by the references and the others are not. So the rest that we see here, this is garbage. So it's taking up space. You can't reach it from any part of your code, but the memory will fill up. So how to get rid of it? Garbage collection. That's the solution. My clicker doesn't work correctly as always. Okay, and before we come to garbage collection, how it is handled in the JVM, we have to take a look what it is. What is it? So it's very simple, right? So it's a form of automatic memory management. There are other forms like automatic reference counting that is used in Swift on iOS and macOS. And it's not the one or the other is better. So it's just different approaches to the same problem. And it identifies and reclaims no longer used memory, ensures efficient memory utilization. And this is the most important part. It frees the user from managing the memory manually. Who did C here in the audience, or C++? Who loves malloc and free, right? It's a pain in the, you know what I, yeah, you know. So, and to understand it, we have to put it in different phases. If we clean up the memory, it's not one simple step. There are multiple steps involved. So if we talk about precise collectors, because there are different kinds of collectors, but if we talk about precise collectors that we have in the JVM, then we have so-called tracing collectors. There's a tracing phase. That means we have to identify all the objects that are reachable. Remember the red arrows, right? So the references from the stack frame to the live objects. So we have to find them. Once we find them, we have to free all the dead ones. And this is a sometimes quite long time-taking process, because we have to check every memory object. Is it free? Is it used? And stuff like that. So we reclaim the non-used memory. And then there's a so-called compaction. Who is old enough to remember Windows 3.11? Oh, yeah. Then all of you know disk defragmentation, right? This is exactly what we do here when we do compaction. So, but I have a demo for you to show you how it works. And then there's something that is called stop the world. You probably heard of that. And some people didn't. So that's the reason why I explain it. Because how it works is, in principle, we have application threads running your application, and then at one point we figure out we have to clean up the heap. So we need to tell all these application threads, you need to stop, right? We send a signal. So if we take a look at the application threads, they start running, then we send the signal for the save point, then it takes sometimes longer, sometimes shorter to stop all the threads. So we stop the threads, and then we reach a so-called JVM save point. All the application threads are stopped. Now we are safe to do garbage collection. Then we have either one or multiple threads doing the garbage collection, cleaning up the heap, and then we resume running the application threads. And this pause in the middle, this is the stop the world pause, right? So if you didn't hear about it, so this is what in the past was a big topic, because applications stop for seconds, and you can't do anything because garbage collection was going on. So this is stop the world. Okay, then now we come to the basic principal collectors. And we differentiate between non-moving and moving collectors. And we start with a non-moving one, which is the most simple mark and sweep. Who heard about mark and sweep? Yeah, most of you, right? It's always simple if you read about it sometimes, but it's more easy if you see it, right? So this is the memory. This is the heap. All the gray areas that you see here is free cells, right? And to make it easy, every object that I allocate takes one of these cells. So if they are gray, they are free. If they are blue, they are taken, and they are not live yet. If they are purple, so they, of course, they are live because they are blue. If they're purple, they are dereferenced. This is dead objects, right? So this stuff is not, you don't have any reference to it anymore. If they have this little red square in the upper left corner, means the garbage collector marked them as live. So he found, oh, this reference is live, this reference is live, this is live. Okay, so he marked these cells as live. If they have a number in it, not in this one, probably, but maybe, it's this cell survived, or this object survived the garbage collection cycle. If it survived 2 times, you will see a 2 and a 3 and so on. So you see on the left side how it works. The mutator, so it means the application allocates memory, and then objects will die. That's the way it is. And then we have to stop the world at some point. Let's take a look at it. So we started, you see, we allocate objects, they get purple, so they die. Until we fill up the heap, at one point we have to stop. In this case, I stopped it when it's really filled up. Then you will see, stop, mark all live objects, remove the old ones, continue. Mark, remove, unmark, continue. This is how it works. And the people who remember Windows 3.11, that's what your disk looked like, right, after some time. That's the reason why you have to do defragmentation. Because you can imagine, in the real world, we don't have each object fits into each cell, right? So we have larger objects. So it gets harder and harder to find continuous space that you can allocate. And we aim for fast allocation, right? This is because that makes the application faster. So you see the problem with this mark and sweep, it's easy because we don't have to move things around, which is great. Once you reference an object, it will stay there forever, so you don't have to move it, which is great. But we have fragmentation. And this is not so nice. So okay, let's take a look at moving collectors. And we have two of them. We start with the so-called compacting collector. And this is just one example. It's mark and compact. It's the same thing that we saw before, right? But instead of just we stop the world, we mark all live objects, we remove the rest, the dead ones, we unmark and continue. In this case, we don't do the continue. We just compact everything to the left side of the heap. So we free up space to have it's more easier to allocate afterwards. So just let's take a look. And now I can't really fill up the complete heap, because when I do compaction, I need some space ahead to move objects around, right? So I stop it when the last rows, now I stop. Mark, unmark, compact, continue. You see the difference. Now it's way easier to allocate memory because it's always free space ahead, okay? So this is if you do mark and compact, which is one of the algorithms that is used in the JVM. But in this case, because we have to move objects around, means we have to update the references. Remember the arrows that coming from the stack frames into the heap? Now when we move objects, we have to update these references. That means after the compaction, we have to update all the references, and then we can continue. Takes more time, but gives us faster allocation. Just a different kind of collector. Okay. We need more headroom, right? So because when we start copy things around to compact, we need a little bit of space, in this case on the right side, to copy things there, free up space, move it back, and so on. Okay, the next one, which is the copy collector, and you will see it's totally different from the other ones, because this one looks like this. So suddenly we have two spaces, right? We have a to space and a from space, and this will toggle. Every time one is filled up, the gray and the orange area will toggle. And so that means the from space becomes the to space and the way around. The idea is if we fill up the left side, right, and you will see that in the demo, then we mark the live cells, we copy them to the right side. And then we know everything that is live was copied. We can just erase the whole left area. So we don't have to check every cell. It's faster. So let's see. So we start allocate, objects will die, we fill up the space, and then at one point when it's filled up, we have to stop the world, mark the live objects, move them to the then to area. You will see it will switch now. Mark, move, erase, continue. Right? Questions afterwards, please. Otherwise we won't make it. The original presentation was 270 slides. So this is 164, and we have 50 minutes. We will make it. So but as you can see, this is, and as I said, this is simplified, right? It's way more complex in the JVM, but this is, you get the idea how it works. You see stuff is copied around. It's easier to just erase, now in this case, the left side, because everything was moved, right? And again, we have to update references. Every time moving objects, updating references. Problem number one. If you have an object that lives for a long time, you copy it all the time, right? That means updating references all the time. It's not that nice. And we need twice the amount of memory here, because we need to be able to copy the whole thing in worst case. Okay, so leads me to the next one, generational collector. And in this case, I use a generational mark and compact. And before we go there, we have to talk about the weak generational hypothesis. And what it means is most objects die young. That's a fact, and it's not only for Java, this is for all languages. And as a simple example, if you define variables in a method, and you call the method, and the method returns, everything that was defined in the method is just garbage, right? So that means these objects live for a very short time. And if you see the chart, then you see that on the left side, we have a lot of short-lived objects. Then we have a few of medium-living objects. And then we have even less very long-living objects. So and if we now shape the garbage collector, the stuff that we saw before, we can shape it now to this behavior. So we take the so-called Eden space, which is smaller, right? because this one contains objects that will die very quickly. That means if it's small, we can really do a very fast collection in this area. So we create objects in this area. Then for the stuff that survived the first iteration of the garbage collector, we have a copy collector here. That's the so-called survivor spaces, because they survived the first garbage collection cycle. Now, in this area, we can copy them for a couple of times, right? And when we see, oh, there are still some objects that are still alive, we promote them to the so-called inert space. This is, in principle, how it works. As I said, simplified. And we talk, they both left the Eden space and the survivor spaces. That's the so-called young generation. And the inert space on the right side, this is the old generation. And if we talk about collections, garbage collections, then we talk about minor collections. This means the young generation. And we talk about major collections, which means the old generation. And if we do a full collection, then it means both generations, right? Sometimes you stumble upon that. You don't have to remember all of this stuff. It's just that you know where it belongs to. Okay, so the idea is collect fast-dying objects as fast as possible. That's the idea. Of course, I have a demo, more simplified here. And you will see we will fill up Eden space, copy the surviving objects in the survivor spaces. And in this demo, when they survive 3 times the garbage collection, they will be promoted to the inert space. And then the inert space, you will see some kind of a wavefront moving through the blue area. And once this is filled up, in this case, we do a full collection. Let's take a look. Okay, we start allocating, objects will die, stop, mark, copy, clean up, and continue, right? Again, so we do this for some time, and then there's a fast forward once we promoted the first stuff to the inert space. I did a fast forward because otherwise it will take minutes before the inert space will fill up. And the idea of the survivor spaces is we don't want to copy stuff around forever, right? So if we really have long-living objects, we move them to the inert space. Now you see the wavefront. Even in the inert space, objects will die. Once this will fill up, we first do a mark and compact in the inert space. Now, check it out on the right side, we will mark all live objects, then we clean the rest, compact, and then we copy everything from the young generation into the inert space. Now, mark, then compact, copy, continue. And then we can start from scratch. So this is in principle how this generational collector works. And I think if you see it, you get some kind of an idea. And the inert space, the reason for it, why this is a large one, it takes long to fill it up. But the collection of the inert space also takes long because this is a big area and we have to free it. That means we have to check every cell. Is it live? Is it not live? And then that takes some time to clean it up, okay? So this is generational collector. Very basic principles. Okay, the question is, I told you we have young generation, old generation. We have different collectors, minor collection in the young, major collection in the old. What do we do if we have a reference from the old generation back to the young one, right? So we have on the left side the young generation, right side old generation. Now we have references, we do a minor collection in the young one. We have references coming from the stack frames, right? And we have also intergenerational references here. And then we have one that comes from the old one and it gets into the young one. But we only do a minor collection. So how does the collector on the left side know about this reference? Because there's no hint. He can't know, right? So in this case, if we don't tell the collector, oh, there's another reference, it will just delete it, even if it's a live cell, and then everything will crash. So, but lucky us, there's a so-called card table, also known as the remembered set, which is an instance in the JVM where the JVM marks these specific references, and then the collector can look it up. So it looks up in the card table, okay, there's a reference from the old generation, the young one, and then he can mark the cell as live and he won't delete it, right? So if you stumble upon card table or remembered set, this is about intergenerational references, okay? So that's all you need to know. You don't need to know the details This is the very basic stuff. We stop the world, everything is serial. What about concurrent? What about doing, I mean, concurrency is hard, we know that, right? So what about if we would like to mark things at the same time where we allocate stuff? Well, let's take a look at it. So, stack frame on the left, this is our route for the garbage collector. And now we start following the references. So we follow to the first one, or we say, oh, this is reachable, awesome. So we mark it live. Next one. From there, we can reach it, oh, cool. So we mark it live. But then suddenly, because it's now concurrent, the application thread decides, oh, you know what? The reference that's coming from the gray one to the lower left, I just remove it, right? I just don't need it anymore because now I put this reference in there. The garbage collector already passed the first white circle. How does he know that the reference was, that there is a new one and that the old one was removed? He doesn't. And what happens is he will just not recognize that this is a live cell now, right? Because the one reference is gone and there's suddenly a new one. So, and that's the problem. So once he finishes, this one won't be detected by the garbage collector. So there is a solution to this problem. And the solution is barriers. You probably, who heard about barriers? That's quite good. Because we have so-called read barriers and write barriers. The only thing you have to keep in mind is this is some piece of code, whatever code it is, that will be executed every time you read an object or you write to an object, right? This is the stuff you should keep in mind. And if we now use it, for example, to track intergenerational references, like the remembered set that we saw, I will have an example how this works. It's also used to synchronize between the allocator and the mutator. So, and the idea is, if you, like I already said, if you access a memory cell either by reading or writing, some code will be executed, right? You have to keep in mind that read barriers are way more, let's say, expensive than write barriers because we have around 75% reads and 25% writes. So which is the reason you would think, oh, I just install a write barrier because then it's not accessed so often. Because if you have code that is, let's say, slow, and you do it in the read barrier, then it takes forever because then it will be executed every time you read a memory cell. So that means read barriers have to be very efficient to work. Okay, we take the same example. We start with garbage collection, but now we install a write barrier on each object. So that means we hit it, it's reachable, we mark it as live. Okay, cool. We went on to the next one. And now the same thing happens. Application thread steps in, but this time the application threads, when he removes the reference, he reaches the write barrier that we installed. And in this case, I told the JVM, if this happens, the old object that was referenced will be marked as reachable. That's all. Not as live, only reachable. That's enough. The collector still has no idea that there was this change. But the idea here is the collector continues to mark stuff, and once he finished, there is a so-called remarking phase. And in this remarking phase, he will find these reachable objects. And so you can get around this problem when you do concurrent marking, right? You can use this read and write barriers. I hope this was somehow understandable because it's a quite complex idea. If you look at the implementation, it's not so easy, but this should give you the idea. You just have to keep in mind barriers are used when reading or writing to objects, and this code will be executed. All right, and in this case, then it can mark it as reachable. So you need a marking phase, and then you do a remarking phase to find all the reachable objects. That's the stuff when you use barriers for garbage collection. The other thing is, now that was marking stuff. If we would like to copy things, right, concurrently, that means you have an object sitting on the memory, and you have all the references pointing to these objects. In this case, again, the stack frames to make it as easy as possible. Now we stop the world, right? Stop the world collector. We copy things, easy. We update all, then we put in forwarding information into the header of the original object. And then we can update all the references to the new one. Once this is done, we continue. This is when we do stop the world. So what if we don't stop the world? Well, then it looks a little bit different. Then it's like we have the object. We don't stop the world. We just copy the object, right? And then we start updating the references. But in this case, both objects are reachable, right? Partly. And that means that threads can access both objects at the same time. Because there's no stop the world here. Application will just continue running. We just copy stuff, update the reference, and suddenly we have this behavior. And which copy is the correct one? Nobody knows, right? So if we would like to do this kind of stuff, one solution that you can use is a so-called Brooks pointer. And the idea is we install a forwarding header in front of the header of the object, right? And then this forwarding header points to the object itself. That's first of all nothing very special. If we then copy the object live, right, and then we install again the forwarding pointer here, let it point to this one, nobody knows about it yet. When we now, before we start updating the references, we just update this forwarding pointer to the new object. And now what happens is that whatever accesses the threads, everything will go to the right object, right? Because of this forwarding pointer in the original object. And we moved it to the new object. That's the idea of a Brooks pointer. And once we updated all the references, and this is something you have to keep in mind, if you work with this kind of copy stuff, then we can't remove the original object until all the references are updated, right? It's not possible because now we need the information. Once we updated all the references, we can just remove the original object and then we can continue. And it's guaranteed that everything will work on the right object in this case, on the new one. So this is concurrent copying. Okay, and now we come to the collectors in the JVM because this is in principle all you need to know to have the basic understanding about garbage collection. But in the JVM, we have all these different collectors, right? So when we start with the oldest one, which is the serial one, and to make it not too long, I have everything on one page in this case. You see, it's available in all JDKs. It's not parallel. It's not concurrent. It is generational. All collectors in OpenJDK are generational except Shenandoah. Shenandoah is just non-generational. Small heap size, longer post times, right? So they can be long. Throughput is low. Latency is a little bit higher. This is a good collector if you work on small systems. Like you have a cluster and you have a node with very small, let's say very low memory or just one CPU. Then this collector is quite good. How it works is, you see it below. You have your application threads, you stop the application save point. You have one thread that does the garbage collection, and then you continue. You can imagine if you have a large heap and you have to do the full collection, then it takes some time before this one thread can really handle all of it. So if you don't select a garbage collector manually, and you have less than 1.8 gigabytes of RAM, or you just have one CPU, the JVM will select this collector for you. It's not the default then, it's not G1. Oh, by the way, who's working on below JDK 8? Okay, on JDK 8 someone? Okay, 11? 17? Okay, 21? Good, 23. Really? Cool. Okay, so just keep in mind, if you don't specify a garbage collector and you work on small nodes, that means less than 1.8 gigabyte or one CPU, you will get this one, right? Just if you wonder why you have these pauses in your application, then probably because you didn't specify a garbage collector and the JVM chooses this one. Okay, next one. Parallel collector, even quite old. It was the default garbage collector from JDK 5 till 8, as far as I remember. It's good for multi-core systems with small heaps. What is that? Oh, just let me shortly interrupt. There's something Okay, so this is, if you need peak performance, this is also called the throughput collector. If we talk about throughput, that's the time you spend in garbage collection versus the time you spend in application. And because in this case, the collector works differently from the serial one, because it doesn't use one thread for the garbage collection, it uses multiple threads. That means the garbage collection pauses can be not so long, right? Shorter. And that's the reason why this is the throughput collector. So it's good if you need peak performance without pause time requirements, because it can have some problems, right? So if you have, for example, if the tenert space, the old generation fills up, then this collector has to do the garbage collection in one garbage collection cycle, even for a large heap. And that can take some time. And that's not predictable. So this is the problem with this collector. But it's good for batch processing, scientific computing, data analysis. It's still a great collector. And it is, like I said, parallel. As you can see, it has multiple threads for the garbage collection, where the serial one just had one. Okay? So it was default from 5 to 8. And then in 8, you could already choose G1, but you have to actively choose it manually. That leads me to CMS. Who remembers CMS? Oh, quite a few. Because this one is already deprecated. So in the current JDKs, you can't even select it anymore. It's a concurrent mark and sweep collector. That was made for have predictable pause times, right? Below a second. I think that was the aim that they tried to reach. This looks very much like the generational collector that I showed you, but it was able to do concurrent marking, for example. So when you do allocation of memory, it could still already mark live objects. But it has some other problems that lead to the fact that there was a successor for this one. It was still good for web application, medium-sized enterprise systems. It was deprecated in JDK, and I have to guess, I think in 9. It was removed from the JDK in JDK 13. So if you are above JDK 14, you can't even switch it on if you use the switch. It's not available. You get an exception there. All right, leads me, oh, and this is how it works. I won't describe it. You see, it gets more complex, and you will see it get even more complex with the other collectors. But you see, we have application threads, then we have initial marking, we have remarking. This is what I mean. We have a first marking phase, and then we have a remarking phase. And we don't go into details here. So it was removed from JDK 14, deprecated in JDK 9, and it does this concurrent marking thing. But it, like I said, it's not available anymore because we have a better one. We have this one, G1. Who's using that? Everyone who said, I don't specify my garbage collector and is more than JDK 9 uses this one. That's the default collector in OpenJDK. And the name is garbage first, and there's a reason for it. And of course, I have a demo, because this one is different from all the others. This is a so-called region-based collector. And the idea is, instead of having these fixed, huge regions, for the tenert space especially, this can really take a long time in the parallel collector to clean that up. So there was the need for having something that is more flexible. And the region-based collector, first of all, the region size, each of these squares, the bigger ones, this is a region, and the size depends on the heap size that you specify. It couldn't get up to 32 megabytes. It can even dynamically grow. It can't shrink. So once it grows to 32, it will stick to 32 in this case. Okay, so you see this is unassigned memory, right, in this case. And then we have these different regions that we remember already. Eden, where we create objects. We have survivor spaces. And then we have tenert regions that are the older ones. And there is a so-called humongous region. This is if the object is larger than half of the region size, it will be directly become a humongous region, which is more or less the same than a tenert space. So we won't copy it around because it's so big. Okay? So we directly get this fixed space and leave it there. In the demo, I don't have a humongous object. It's to make it more simple. Here's my demo. We have 6 Eden regions, that's the yellow ones. When we run out of this space for the 6 ones, we take the 2 that have the most garbage in there and copy all the live objects into a survivor region. And then we continue with this. So we have 3 survivor regions, and then we will see how this works. So we allocate first Eden region full, second one, now objects start to die, getting older. And now it's 4, 5, and when the 6th one fills up, we take the 2 with the most garbage and copy them. Already happened. In this case, 2 survivor regions. And so we continue, right? This is how it works. And a region is not fixed to be an Eden region. Could be a survivor region, could be a to-nerd region later on. That makes the whole thing very flexible, right? And as you can see, it's not that bound to these fixed areas as the other collectors have been. So this is the case why this collector is quite popular. This is the reason why it became the default collector, and it seems to work for most of you, right? Because it's good. Okay. Yeah, as you can see, it goes on for some time. We don't have to wait for it. It will just continue forever, but to get an idea. So it's good. You have to choose it when response time is more important than throughput, and the pause time should be around 200 milliseconds. That's what they aim for with G1. Could even be faster, but there are lots of switches to define that. Heap size, it's perfect around 16 to 32 gigabytes. If it gets bigger, then it's not optimal, right? It will work, of course, but there are other collectors that are better for bigger heaps. So for mixed workloads, large size enterprise system responsive in medium or large heaps, it's a good one. You see, it was available from JDK 7 update 4 and onwards. It is parallel, partially concurrent, and generational, of course. If you follow it, the heap size is medium to large. The other ones have been more for smaller ones. Pause time is short to medium. Throughput is high. Latency, not that good, but still totally fine. I say not that good because we have better collectors for this kind of stuff. Okay, this is how it works. I don't go through all the arrows. So you get the idea. It gets really complex, and this is just a simplification to give you an idea how it works. Important, this is the default collector right now, and it might stay for some time. Maybe we will see ZGC as the default one, and it can do a partially concurrent marking in this case. Leads me to epsilon. Who knows this one? Oh, that's quite a few people, because this is the non-collector collector. Strange. It's a garbage collector that doesn't do garbage collection. So you might ask yourself, okay, what's the reason for this stuff? Well, the reason is, just think about it. If you measure your application performance, for example, you always measure also the garbage collector that steps in, and you can't really predict when it happens, right? So that means you have to run the stuff a couple of times to get some medium value out of your results. If you just would like to know how good your application performs, you can use this collector, which doesn't do any garbage collection, but that also means you really have to know how much memory you need, because otherwise it will run out of heap. So you specify the heap, and once it fills up, you get an out-of-memory exception. But that could also be very beneficial if you have very small services and you would like to have the highest possible performance, and you know exactly how much memory it needs. You can use this collector because then you have never garbage collection, right? So it's good if you need extremely short-lived jobs, or if you need last drop latency improvements or throughput improvements. Then this collector is quite useful. But be careful, like I said, there's no garbage collection at all. If you run out of memory, then it's game over. And you will see this can be very quickly. It's available since JDK 11, and it's always worth looking around or playing around with this thing. It's only in builds of OpenJDK. So is someone using OpenJ9 or Tamarin? Not Tamarin, I mean Samaru from IBM here in the audience. Okay, because they have different collectors. They work differently. They don't have something like this. And to be honest, I don't know exactly the names and how they work. Leads me to Shenandoah. Who knows Shenandoah? Okay, is someone using Shenandoah in production here? Nobody? Okay. This was developed by Red Hat. Roman Kenke was one of the developers of that, but he left. He's now at Amazon. And maybe this is the case. We never saw a generational version of that. So this is non-generational. But it's a very good collector. It's made for very large heaps, so 100 plus gigabytes. And I think they guarantee response times below 10 milliseconds, which is quite good. So that means the worst thing you can get is 10 milliseconds of garbage collection pause. That's quite good already. So if you have applications that are really sensitive to latency, or you have a large-scale system, highly concurrent applications, this is a quite good collector. This one is not available in Oracle JDK. Is someone using Oracle JDK here? Okay, so sorry for you, you can't use it. It's not available there. I don't know why, but yeah. You have to keep in mind, as soon as you do fully concurrent garbage collection, there's always a drop in performance. And the reason is you have, let's say, 10 application threads, and you do stop the world garbage collection. Then you have 10 threads, you stop it, you do the garbage collection, again you have 10 threads for the application. If you do concurrent garbage collection, then from the 10 threads, you might have only 9 or 8, because the other ones are used to do the garbage collection at the same time. That means you will see a drop in performance when you use a fully concurrent garbage collector, that's for sure. And that's also one of the reasons why it makes sense to use this kind of garbage collectors that we will see now in really, if you have a lot of memory, big heaps, if you have a lot of CPU, then these collectors really shine. They can handle smaller heaps, but it's not really optimum for there. ZGC. Is someone using that in production? Okay, good. The name is wrong. It's not Zero Garbage Collector. I thought it is the name, but it's not. So this is, in principle, the heap layout. So they have old and young generations. In the meantime, because up to JDK 21, ZGC was only non-generational, and you could switch on a generational version. Now, from JDK 23, there's only the generational version. The non-generational is already deprecated, so that means it will go away. The reason for that is that the generational one the performance is way better, right? So that's the reason. Because you can allocate the young objects faster. So there's no reason. If you have a non-generational, you have to always do everything, and that takes just longer. That's the reason why the generational one is the preferred one now. Okay, I won't go into detail with this one, because the next one that I have, this is more or less a copy of the next one, which most of the people don't know. So this is available from JDK 15, that was the non-generational, and then we got the generational in 21, which is now the default if you use JDK 23. This is made for response times below a millisecond. So it's even faster than Shenandoah, right? So it means the worst pause times that you will see is 1 millisecond, which is more or less nothing. That's what many people say, this is a pauseless garbage collector, which is more or less true. But even the pauseless garbage collectors have these very small pauses. So it's made for heap sizes up to terabytes, right? And if you need predictable response times, this is the way to go. So if you have low latency systems, large-scale systems, high concurrent applications, very good collector, but it needs more memory, more CPU. Keep that in mind. It works with smaller heaps, but not that good. So then you can better choose G1. It might become the default collector in the future. I'm not sure about that, but I heard it. I think I read it somewhere. So this is, I'm not sure. And like I said, non-generational will go away. I think within the next versions at some point. That leads me to the last one in the row, which is C4, Concurrent Continuous Compacting Collector, which is the collector that Azul invented. And ZGC, especially the non-generational one, is a one-to-one copy of this collector. So it's exactly the same thing. Different names, same principle, exactly the same algorithm. So that means everything I say now also applies for ZGC. So this is only available in Azul Zing, which is our own JVM. And it makes use of loaded value barriers. That's read barriers, right? Everywhere. And we only need one CPU cycle to execute the code. I told you read barriers have to be very efficient to really make it work. And so for us, this is one CPU cycle that we need to execute every time you access a memory cell. And this is more or less the same for ZGC. So if you work on Linux, then it's a good idea to enable transparent huge pages, because then this has an impact on the memory pages, on the region size. Come on. So to give you an idea how this works, and as I said, same as in ZGC, we have multiple garbage collection threads. You see the squares, again, this is the roots, the stack frames in this case, and we have the references to the heap where we have the objects. So we mark all these objects, and we have the loaded value barrier, which is the read barrier, on all the objects installed. So garbage collector follows all these references through the heap, and then suddenly the application steps in and allocates a new cell. And now the big difference is, once the application thread is doing that, it hits the loaded value barrier, and that leads in this case to the fact that it will mark the cell, right? So it will do the test and jump, the one CPU instruction will mark the cell, and then it will pass it to the garbage collector. So in this case, the mutator and the collector working hand in hand using these read barriers. That means the collector doesn't have to do a remarking phase because the allocator already marks the cell. Right? This is the big difference here. And that leads to, you don't have to do the remarking phase. That saves time. It's just faster. And the garbage collector can just continue working, doing the collection. Another feature is the so-called quick release, which is also quite interesting. If we have the regions there, which is virtual memory, right? And below that we have physical memory, because the JVM only works with virtual memory. But in the end, somewhere you have hardware, right? Really physical memory. So now we start and move things around. So we compact in this case. So we move objects from one page to another. And in this case, and also for ZGC, the forwarding information is not stored in the header of the original object, but we store it outside in an off-heap memory area. This is fixed. It's always the same area. So, and we do this for all the objects, right? And we continue. So once we marked all this stuff, we can directly, because there's no mapping in the original objects anymore, we can directly remove the physical memory and just allocate it for, or take it for new virtual memory. This is quick release. With the other approach that I showed you with the pointers and the forwarding pointers in the headers, we have to wait until all the references have been updated before we can really free the physical memory. Here it's directly, because the forwarding information is outside of the object. That's so-called quick release. All right, I know this is a lot of stuff. You don't have to remember all of it, but most of it is, I think, quite useful. Same as with ZGC. Right? It's good for very large heaps. We have, for example, one customer that has I think it's around 20 terabyte heap, and they still have 0 garbage collection pauses, means below 1 millisecond. This only works on systems where you have lots of CPU, lots of memory. Then these collectors really shine. All right, this is only available in Azul Zing JVM. We have the benefit that we not only have the collector, but we also have our own compiler, which is faster, so we don't really see the drop in performance because our compiler creates faster code, which makes it beneficial if you compare it against, for example, plain OpenJDK using ZGC. The garbage collector is as fast as ours, but the compiler is faster. So now I showed you all the different garbage collectors. Big question is, which one to choose, right? For this, we have 3 essential criteria, which is throughput, latency, resource usage, which means memory footprint, more or less. So the good thing is you don't really have to choose all of them, because you can't really. In principle, you can choose 2 out of 3. This is how it works, right? So you can say, I would like to have very high throughput and very low latency. You won't get low resource usage, sorry. Or you can say, oh, I need low resource usage and very low latency. Sorry, it won't have high throughput. This is more or less how it really is in reality. And to make it easier for you, I created this chart. And I saw that this is more or less a copy that I found in a Red Hat presentation, but it's just good because it shows exactly how it is. If you prefer low pause times and you can live with runtime overhead, that means you have enough CPUs, you go to the left side of the spectrum, right? If you say, no, I really don't have enough resources, I can't really handle runtime overhead, I can live with longer pauses, then you go to the right side. And you see in the middle already there's G1, which covers most of it, and you saw that most of you just use the default, that means it works for you. But it's always good to know that there are these 2 places, right? The high performance space, and also where you don't really care about the garbage collection pauses. And you need to make a decision. And to give you an idea, I just created an overview where you have all these collectors with all the different features that they have. And then it should make things easier to select the right collector. But usually, if G1 works for you, great. You don't have to change it, right? Just because Netflix switched to ZGC, you don't have to. Not every one of you is Netflix. And I think they saw a performance drop of 3% compared to G1, if I'm right, because there was a blog post about that. So, but you can, at least you can give it a try. So, right, so this is not that you shouldn't do it, but if you don't see any problems, there's no need for it. All right. With this, I'm done. I hope I'm on time. Probably, I don't know. If you have any questions, you can reach me outside, because I think time is over, if I'm right. Thanks.
All systems are nominal. Initialize Genesis sequence.